today. Here we go. Okay, gang, today's video is on dynamics on impulse and momentum. Okay? Impulse and momentum. What in the world is that? What is an impulse, right? An impulse is, well, it's just a force over some amount of time, okay? So we can think about it's some force times some amount of time. That is an impulse, this guy here, okay? And generally we see that in dynamics when we're talking about collisions. Two things running into each other. There is that force over some period of time that causes some reaction after that, okay? Now, what we can also have here is on these things, there's two things. We have, number one, the conservation of energy. And number two, we have conservation of momentum. Okay? And in most of these problems, here's what's going to happen. Momentum is going to be conserved, okay? The amount of velocity and mass going into the system is equal to the amount of velocity and mass going out of the system, less some whatever's lost in this impulse here. Now, conservation of energy. Is energy conserved here? Mostly, but not totally, because there is some energy lost in heat and friction, and so energy not totally conserved. So on these problems, we will not use this guy here, but we will use conservation of momentum, okay? And the equation that we're going to use for this is this. M1V1, okay? Or you could call it initial and V initial, right? Plus Ft, this is the impulse, is equal to, now I'm gonna put it like this. I'm gonna put the sum of M2 V2s, or instead of twos, let's just put a little F there for final. So we've got the initial mass times velocity plus the impulse. So this here's momentum, okay? Momentum coming into the system. This is the impulse. And then this here is the momentum final, or the momentum leaving the system. And notice there's a sum there. We'll do that especially when we talk about this, okay? We're going to talk about a couple of problems, okay? Number one, we're going to talk about, well, I guess we can do that one first. Doesn't really matter. But this is, the bullet striking the block example. It is just a classic, okay? Probably every dynamics book ever written has this problem in it. There's something coming into it, it hits an object, and then after that, it passes through the object, and then what's happening afterwards, okay? We'll look at that guy. And the other is, there's some kind of impulse, some kind of striking force, whether it's a foot on that's the soccer ball, y'all. I drew that, okay? Y'all might call that a football, but you'd be calling it wrong, because that's not what a football looks like, okay? America. All right. Once the foot impulse, there is some force over amount of time that creates a collision here that makes this guy want to leave the scene, right? Now we're saying here that this ball is going to leave at 35 degrees, okay? So find the impulse on the ball when it's kicked at 35-degree angle, okay? The ball travels 30 meters in the air before landing back on, and I did that for you. I called it the pitch, okay? We just call it the field here, but whatever. Okay? So, you know what that sounds like to me? That sounds like projectile motion, doesn't it? I mean, now we're going to assume that the pitch is flat, and when the ball goes up, the ball comes down, and it lands at the same height that it took off at, okay? So that's pretty easy to say, okay? So we'll work that problem first, okay? Then we'll come do this one second. We'll show you how to do that problem, okay? Okay, one other thing that you got to remember on impulse problems is direction matters, okay? So direction does matter. So let's see what happens when this 500 gram, I don't know if that's regulation soccer ball size. I just made that up, okay? So I'm sure I'll get a comment that tells me the real size of a soccer ball. But anyway, okay. Let's see if we can solve this, okay? So let's look at our equation here, okay? So the ball, does it have an initial mass? The answer is yes. Does it have an initial velocity? The answer is, well, yes, it's 0 though, right? The ball was just sitting there on the turf. And so for the very first part, this whole bit here is going to be 0. Okay, now this is what we're looking for, find the impulse. So we're looking for this value right here, okay? And so the impulse is equal to the mass final. Well, when I kick the ball and it goes over to its final place here down the field, right? What's the mass over there? Same as it was when it started, okay? So, impulse, this thing, is equal to, now I said the sum, right? Sometimes you might have a collision where the two things bond together, right? So now it's this thing plus that thing. So you would have a sum. In this case, there's no sum there. We could ignore that because we just have one ball, okay? So the mass is 500 grams, or let's see, how about 0.5 kilograms, okay? Times V final. Now, how in the world can we find that? I don't know. Oh, yeah. What is this? What do we say that was? That's projectile motion. Is it constant? Can we use our constant acceleration equations? Let's see. Remember, we have to break that into components, right? We've got a component here, and we've got a component here, right? We've got a y component, and we've got an x component. Well, in the x component, once the impulse is done, there is no more acceleration in the x, right? In the y, we have one acceleration, and then that is gravity sucks, right? 9.81 pulling down on it. So let's use our equations. We're going to need two of them, okay? So in the x direction, okay, and then we'll have the same equation for the y direction over here, right? And what we're going to use is, I think we'll use our position equation from projectile motion. Do you remember, or has it been too long? It really hasn't been that long, has it? It goes like this. S final equals S initial, remember S is position, plus V T times plus 1/2 AT squared, right? Okay, and this is the initial velocity. And of course, this is in the x direction. We're going to have this, same thing over here, okay? S final equals S initial plus V initial times T plus 1/2 AT squared. Okay, so let's try this guy. Now, remember, here is V sub I, right? Boom! Its initial velocity, it's at 35 degrees, right? It's at 35 degrees. So the x component of that guy is what? It's V initial times the cosine of 35. And this guy is V initial times the sine of 35, okay? So that's going to be our initial velocity that we're going to use here. So the final position, the final position, right, if I call this 0, the final position was, well, it said it somewhere. Oh, there it is, 30 meters, right? So 30 meters is equal to initial position, that's 0, okay, plus, what is this guy right here going to be? This guy is going to be, that, right? V sub I cos 35 times t, okay, plus, what's the acceleration in the x direction? That's 0, Let's go over here to the y direction. Okay, the initial position in the y, in elevation, let's call it 0, right, initially. Its final position, it landed back on the same field at the same height. We'll call that 0, okay? This guy's 0. And we've got this guy, right, which is v sub I sine of 35 degrees plus, let's just move that, plus 1/2 a, well, a is negative 9.81 meters per second squared times t squared, okay? Cool. Now, should you be concerned that we're looking for v final here, but we have v initial here? The answer is no, because the impulse, the velocity, is what is that velocity just as the impulse is over with, right? What is the initial velocity here, or the final velocity once the impulse has been applied, right? Which is the initial velocity for the projectile motion part, right? So the initial of this is equal to the final of that, okay? So to lessen the confusion, let's just get rid of that I and get rid of that I, and we'll get rid of that F, okay? Because that V is the same V as that V. That's what we're searching for. Now look what we've got. We've got two equations with two unknowns. Dude, we're there. Let's solve this guy for T, okay? So T equals, oh, I don't know, 30 divided by V cos 35. Okay, now this guy over here, ooh, that's half of 9.81 is 4.905, right? T squared is equal to V times the sine of 35. Oh, I left a T off, didn't I? There's got to be a T right there, doesn't there? Oh, probably I get 12 emails. You forgot the T. No, I didn't. There it is. There it is. Don't panic. Okay. Now, one thing we can do right here is I could divide both sides by T, couldn't I? Okay. Let's get rid of that guy and one of those guys. Now, let's take that T and substitute it in there, and we get 4.905 times 30 over V cos 35 equals V sine 35. Okay. Oh my goodness. So wait, let's see. On 4.905 times 30 equals divided by the cosine of 35 equals 179, and then divided that by, let's divide that by sine 35, right? Divided by sine of 35 equals 313.18, or 313.2. Is equal to, now I still have a V on the bottom, I'm going to multiply it on the other side and get, look here, equals V squared. Okay? Equals V squared. So our velocity of the ye old football, or soccer ball, is going to be that number square root, right? Square root answer equals 17.7. Okay? So V equals 17.7 meters per second. Remember, this was in meters and our time is in seconds. So boom, now we have V. Now all that's left to do is take that V, come plug it right back in here. Let's plug it right there. And we get 17.7 meters per second. Okay, so times 0.5 is 8.85. 8.85. And here's the units, right? Kilogram meters per second. Okay? Now that's not a joule or a newton. That's the units of impulse, right? Because what's the units for mass times velocity? Well, that's kilograms, and that's meters per second. So that's the same as that, isn't it? Now remember, one thing I told you is impulse direction matters, and so we need to put this on there. Bloop. Let's put that on there at an angle of 35 degrees, okay? And now that's complete, okay? Now, if you wanted to, you could break that into components and you could tell how much of the impulse is in that direction, how much is in that direction, but this is at 35 degrees, okay? All right. I hope that makes sense. That's way number one. Let's erase this and let's see if we can do way number two. Problem number two. Now, I erased everything. I erased a lot, didn't I? That's a P and that's an A, right? But I should have, or I could have, left our momentum equation up here, which is m1v1 plus ft, the impulse, is equal to sum of m to v2, okay? Now, what we want to do is the same thing, okay? The bullet goes and it hits the block. The instant that it leaves the block right there, okay, we'll consider it, the two things are still together, right? I know that this is going to separate because this is going to move slower than the bullet when it leaves the block, but the instant right there before it leaves there, right? What is the velocity of that whole system, which would be the initial velocity of this block? Now, every second after that, this block is going to be slowing down because of friction, right? And of course, the bullet's going to keep continuing out there, but it's going to start dropping because of, well, gravity, right? Okay? So, let's see if we can do this, right? So, right before it leaves, we're going to consider the bullet and the block are still together, okay? So what you have is, number one, you have m1v1. Momentum is conserved, okay? So you have this, 1,000 times 20 grams. Now, what is 20 grams? That's 0.02 kilograms, isn't it? I want to get everything into the same units, right? Which is, the 1,000. Oh, eraser. Right? Is 1,000 meters per second. Notice this, right? This is kilogram meters per second. What did we say the units for that was? Kilogram meter per second, right? It's like apples plus apples, right? Now, in this case, this guy here is 0, okay? Over there, I didn't know about the initial, the weight of the foot, the initial thing that was giving it, right? I was trying to find the impulse there, okay? This one, I know the initial, the thing that's causing the impulse, okay? I know this guy. Okay, so this is going to be 0, this guy over here. So the things coming in equal the things going out, right? Conservation of momentum. The speed times the mass coming into the system is the same as the speed times the mass going out of the system. Okay, so over here, what do we have? Well, I'll tell you what we have. We have two things. We have the weight of the bullet and the weight of the, the block, okay? So let's do this. The block, how fast is the block moving? The block is going to be moving, I don't know. Mass, 25 kilograms, times the velocity of the block, I don't know what it is, okay? I don't know. It's kind of what we're looking for. How fast is the block going? Plus, here's the other momentum, right? The bullet, which was 1,000, right? 1,000. It was 20. It was 0.02 kilograms times how fast? Well, I'm running out of room here, y'all. I have to move my bullet over. Times 250. Okay? So I should be able to find, I know the velocity of the bullet, it's right at the instant it leaves there, right? It's going 250. Because like I said, the one instant after that, this guy's starting to slow down already, okay? So here we go. Let's see, 1,000, where's the calculator? All right, 1,000 times 0.02. Oh no. Well, it's 20. We knew that already, didn't we? 20 is equal to 25V plus 0.02 times 250 is 5. Okay, subtract off 5 over there, 15 divided by 25 equals V. V equals, okay, let's see, 15 divided by 25 equals, that is not right. 15 divided by 25, I think I hit times, 0.6 meters per second, okay? So it's not going very fast, is it? But 0.6 meters is like, what, 3 feet in a second? It's not going very fast, is it? The bullet was just so little, he just blew right through there. So this guy was so heavy, right, 25 kilograms in relation to this little bitty lightweight bullet, I forgot what he was, 20 grams, that it just didn't move very much, did it? Okay? Now that's not the answer, right? Because what is it asking us for? Find the speed of the block as the bullet exits. Well, that's that, right? That's the speed of the block. That's in velocity. As well as how long it will take it to come to rest. Well, we can use conservation of momentum for that as well, okay? Let's see if we can do that as well. If we have, here's our equation for conservation of momentum, or for the momentum impulse equation, right? If we have this, right, how long will it take? That's time, right? We're looking for that guy right there. So do we know the final velocity? Methinks it is 0, right? So all of this is going to go to 0. Now, in this case, this over here is not 0, is it? This time, this is not 0. Okay? Okay. We have this. But this doesn't make any sense. I mean, one of these two things, if I move it to the other side, if that's 0, one of those two things has to be negative, doesn't it? Well, what's slowing the block down? Friction, right? Now we're given the coefficient of friction over here is 0.25. Which way is the friction going? Well, friction is going to oppose the motion. There it is, the friction force, which is mu times N, right? Okay? It's going to oppose that force. So friction is going to be working in the opposite direction of motion. So guess what? That friction force vector is going to have a negative sign. So that's going to be a negative sign. So when I move him to the other side, boom, he becomes positive. So I get this. I get Ft equals M1V1. Okay? So, number one, what is F? What is the force that is acting over time, that impulse force, to cause the thing to stop? Well, it's friction force, right? And it wouldn't be a dynamics problem if we didn't work this little guy right here in. There he is. There's the force. And he's equal to MA, isn't he? Okay, there it is. There's your dynamics equation. So, 25 times 9.81, 25 times 9.81 equals a force of 245.25, 245.25 newtons, right? Times, that's the normal force pushing down on the floor, right? Box push on floor, floor push on box, times 0.25 equals a friction force of 61.31 newtons, okay? 61.31 newtons. And what's a newton? Kilogram meter per second squared, okay, equals, okay, the mass. What's the mass? 25 kilograms. And what was the velocity? We had the velocity, didn't we? Right there. The velocity times 0.6 meters per second. Okay, so what's that going to do? 25 times 0.6 equals 15 divided by 61.31 equals T equals 0.245 seconds. Not very long. That's how long it takes to come to rest, okay? All right, there's an introduction to impulse and momentum. Man, I hope this helps you. Before we leave this